Hey tech enthusiasts, welcome back to VLSI Verse, where we dive deep into the world of cutting edge technology. Today, we're tackling one of the hottest debates in the tech space: CPUs versus GPUs versus NPUs. What are they, how do they work, and most importantly, which one is the king of performance? Let's find out. First, let's break down what each of these acronyms stand for and why, what they do. The CPU, or Central Processing Unit, is the brain of your computer. It handles general purpose tasks like running your operating systems, web browsers, and more. The GPU, or Graphic Processing Unit, is your go-to for rendering images, video editing, and games. And then we have the NPU, or Neural Processing Unit, a specialized chip designed to accelerate AI machines learning tasks. But how exactly do they differ? Let's start with the CPU, or Central Processing Unit. Think of the CPU as the brain of your computer. It's responsible for executing instructions from programs, managing the flow of information, and performing arithmetic and logical operations. Modern CPUs are composed of multiple cores, each capable of handling separate tasks simultaneously. This parallel processing capability has a significant advancement, allowing for better multitasking and performance. In addition to cores, CPUs have caches, small amounts of memory located on the chip itself, to speed up access to frequently used data. The CPU operates on an instruction cycle, fetching an instruction, decoding what needs to be done, executing the task, and then storing the result. This happens millions of times per second, which is why CPUs are recently central to everything your computer does, from opening a browser to running complex software. Thanks to VLSI, this entire process is optimized at a microscopic level. Now let's turn our attention to GPUs, Graphic Processing Unit. A GPU is a specialized microprocessor designed to handle and accelerate the rendering of images, videos, and animations. While originally designed for rendering graphics, GPUs have evolved into power parallel processors that are now used for a variety of computations tasks beyond graphics. GPUs differ from CPUs in their architecture. While a CPU has a few cores optimized for sequential processing, a GPU has thousands of smaller, more efficient cores designed for parallel processing. This architecture makes GPU ideal for handling tasks where many calculations can be performed simultaneously. Example: NVIDIA cores. In NVIDIA GPUs, cores are the units which perform the parallel processing. A high-end GPU like the NVIDIA GeForce RTX 4090 can have over 16,000 such cores, allowing it to process thousands of tasks at the same time. Second example is graphics rendering. The primary function of a GPU is to render graphics, especially in 3D applications. This involves a range of tasks such as drawing pixels on the screen, applying textures, and calculating lighting effects. Example: a real-time ray tracing in games. Modern GPUs like NVIDIA RTX series use ray tracing to simulate realistic lighting reflections and shadows in real time. This technology allows games to have incredibly detailed and lifelike graphics. GPUs are also used for parallel computing and general purpose GPUs, that is GPUs. GPUs excel in parallel computing, which involves breaking down complex tasks into smaller, independent tasks that can be processed simultaneously. This has led to a rise of GPUs, where GPUs are used for general purpose computing tasks as well. Examples are deep learning and AI. In deep learning, neural networks require vast amount of data to be processed simultaneously. GPUs are widely used for training AI models because they can perform multiple operations in parallel. For instance, a model like GPT-4 was trained using GPUs to process enormous datasets efficiently. Next example is cryptocurrency mining. GPUs are popular in cryptocurrency mining because they can efficiently perform the repetitive complex calculations needed to verify transactions on the blockchain. Next, video editing and rendering. GPU accelerates the video editing process by handling tasks such as rendering video effects, transitions, and color grading. Example is Adobe Premiere Pro. In video editing software like Adobe Premiere Pro, the GPU accelerates rendering and playback. When applying effects like color correction or transition, the GPU processes these effects in real time, allowing editors to see changes instantly without waiting for the entire video to render. Next, we also use GPUs for scientific research and simulation. In scientific computing, GPUs are used to perform simultaneous simulations and analyze data that require significant computational power. Example, molecular dynamics. It's also used in autonomous vehicles. GPUs are crucial in the development of autonomous vehicles, where they process vast amount of data from sensors and cameras in real time to make driving decisions, like Tesla's full self-driving systems. Tesla's autonomous driving system relies heavily on GPUs to process visual data from cameras and interrupt the surrounding environment and interpret it, enabling the cars to navigate and make decisions automatically. So what does VLSI play the role in GPUs? So VLSI technology enables the integration of thousands to 10,000s of processing cores on a single GPU chip. These cores are interconnected through complex networks, allowing GPU to handle multiple tasks at once. NVIDIA GPUs, this is possible because of the high transistor density achievable through advanced VLSI techniques such as 5 nanometer or even 3 nanometer processing nodes. Memory integration and bandwidth. One of the critical challenges in GPU design is providing high memory bandwidth to feed the parallel processing units with the data. VLSI technology allows the integration of advanced memory technologies like GDDR, GDDR6X, or the upcoming GDDR7 directly onto the GPU die, reducing latency and increasing bandwidth. The GDDR7 is upcoming GPUs. The NVIDIA RTX 5000 series is expected to feature GDDR7 memory, which offers significantly high bandwidth than previous generations. This memory integration is made possible through advanced VLSI techniques, which allows efficient packing and power management of these memory modules. Power efficiency and thermal management. As the number of transistors on a GPU increases, so does power consumption and heat generation. VLSI design is GPUs focuses on optimizing power efficiency and managing thermal output to ensure that the GPU can operate at high performance without overheating. Techniques such as dynamic voltage and frequency scaling, power gating, and advanced cooling solutions are integral parts of VLSI designs for GPUs. Advanced fabrication techniques. The push towards smaller fabrication nodes, example 5 nanometer, 3 nanometer, 1 nanometer, is a direct result of advancements in higher performance and efficiency. However, designing at these scales also presents challenges like managing quantum effects and ensuring reliable operation, which VLSI engineers must overcome. So, VLSI is the backbone of modern GPU design, enabling the integration of a vast number of transistors, advanced memory systems, and efficient power management techniques onto a single chip. The continued advancement in VLSI design are what allows GPUs to keep up with the growing demands for high performance, efficiency, and specialized computing tasks. Now, let's explore NPUs, Neural Processing Units. In computing, neural processing units are specialized processors designed to accelerate machine learning and artificial intelligence tasks, particularly those related to neural networks. These processors are optimized for handling massive amounts of data and complex mathematical operations such as matrix multiplications and convolutions, which are fundamental in AI applications like image recognition, natural language processing, and autonomous systems. Matrix multiplication in deep learning. Matrix multiplication occurs in layers of neural networks where the input data is multiplied by weights. NPUs are optimized to perform these operations much faster than traditional CPUs. NPUs are changing the game in the world of tech. You might have heard about CPUs and GPUs, but NPUs are the new heroes of AI. And the magic behind them is VLSI technology. Again. So buckle up. We're going to go on a wild ride into the heart of AI processing. Without VLSI, NPUs wouldn't be possible because they require massive parallel processing power to handle all those AI tasks like image processing, language translation, and self-driving algorithms. VLSI is literally making sure that we can fit all the AI juice into small power-efficient chips. Let's go to some examples, shall we? Example 1. Apple's neural engine in your iPhone. You've probably heard of Apple's neural engine, right? That little NPU inside your iPhone is what makes Face ID work and power real-time photo enhancements. What's incredible is how efficient it is. Thanks to VLSI, Apple can fit 600 billion operations per second into a chip so small it fits in your pocket. Imagine, without VLSI, your phone wouldn't be able to handle AI tasks on device. It would need the cloud, which means slower performance. So next time you unlock your phone with Face ID, remember it's VLSI and that neural engine working behind the scenes doing crazy amounts of processing to make sure you can instantly unlock your phone. Example 2. Google's TPU, Tensor Processing Unit. Now let's shift gears to Google's TPU. This one lives in the cloud. Google uses its tensor processing units to power things like Google Translate and Photos, performing lightning-fast AI computations. Think about it, without VLSI, Google's TPU wouldn't be able to handle the massive amount of AI-driven research queries and image recognition that you rely on every day. When you upload a photo to Google Photos and it automatically categorizes people or places, the TPU is doing all the heavy lifting. VLSI makes it possible to run millions of tasks in parallel, enabling Google to train and deploy AI models at blazing speeds. NPUs are integrated circuits, but they differ from single function ASICs. While ASICs are designed for a singular purpose such as mining Bitcoin, etc. NPUs offer more complexity and flexibility, catering to the diverse demands of network computing. For most consumer products, the NPUs are actually integrated into the main CPU as the Intel Core and Core Ultra series or the new AMD Ryzen 8040 series laptops. These NPUs are discrete processors in large data like a motherboard. NPUs are becoming increasingly common in the PC and laptop domain. Intel Core Ultra processors and Qualcomm Snapdragon processors are examples where NPUs are integrated alongside CPUs and GPUs. Qualcomm's NPU, for instance, can perform an impressive 75 tera operations per second, showing its capability of handling generative AI. Why NPUs over GPUs or CPUs? What's different? You might be wondering, why not just a GPU or a CPU for AI tasks? Well, NPUs are specifically optimized for the kind of operations that neural networks require. And that's why VLSI design comes in, giving NPUs the architecture they need to outperform CPUs and GPUs in AI tasks. So CPUs are great for general purpose tasks. GPUs are amazing for parallel processing and graphics. NPUs, they are super efficient for AI workloads. And with VLSI, they can do it with much less power consumption. Let's move on to the next example, Tesla's FSD chip for self-driving. Oh, and don't even get me started on Tesla. Their full self-driving chip is a beast, packing 2 NPUs into one chip, processing 36 trillion operations per second. This is how Tesla vehicles can handle tasks like lane recognition, obstacle detection, and decision making, all in real time. Thanks to VLSI, Tesla can pack this kind of power into a compact chip, allowing the car to make split-second decisions. Next time you see a Tesla zooming by an autopilot, just know it's VLSI-powered NPUs processing tons and tons of data from the vehicle sensors, making sure it drives safely. Fourth example is NVIDIA's Jetson Nano for Edge AI. One last example I gotta mention is NVIDIA's Jetson Nano. This little powerhouse is used for Edge AI, basically performing AI tasks without needing a massive data center. It's perfect for things like smart cameras, drones, and robots, with VLSI allowing Jetson to perform AI tasks at ultra low power. Devices can make real-time decisions on the spot. Imagine a drone flying autonomously, dodging obstacles and finding its way, all thanks to an NPU running on minimal energy. That's VLSI in action. NPUs are continuously evolving with advancements in the number of processing cores, memory, bandwidth, and integration into various devices. Huawei's Kirin 970, this was one of the first smartphone chipsets to integrate an NPU, providing 25 times better performance and 50 times greater efficiency in AI tasks like image recognition compared to CPUs. VLSI is like the invisible superhero of the tech world, enabling the creation of smaller, faster, and more efficient NPUs that power everything from your smartphone to self-driving cars. It's why NPUs are becoming the go-to solution for AI processing, with real-world applications in autonomous vehicles, smartphones, edge computing, and much more. Whether it's Tesla's self-driving chip, Apple's neural engine, or Google's TPU, the common thread is VLSI, making it all possible. So, if you're excited about the future of AI, just remember it's VLSI and NPUs leading the charge. Thank you, and don't forget to like, share, comment, subscribe if you found this breakdown helpful. Leave a comment below on what tech topic you would like me to dive deeper into next.